Now, I'm very pleased to introduce a friend of mine from the Surrey Space Centre down at the University of Surrey in Guildford. Chris Bridges is, like Sean, one of the next generation of space scientists who's going to tell us about what next. Over to you, Chris.
Thank you very much, Stuart. If only my students actually started applauding as I'm about to give a talk, that would be good, rather than having some sort of static interface. So I've got to follow now an astronaut and, of course, a very esteemed colleague as well. So what do I tell you about myself? I'm a radio amateur, that's why I've got this weird code kind of on my slide you can see here, M0IEB. That means I'm one of those sort of people that has a walkie-talkie, and we often sit with radios, talking to people across spacecraft. But it also means as well we get to get involved in things like Tim Peake's Principia mission as well. And we were able to help at the Space Centre with getting some voice communications. I was able to go out with the ITRS team as well, with AMSAT UK, to kind of do that thing. That's about as big a claim that I can kind of make to some of those things. But I have the brief of talking about really what is next, what are we going to see, what are we going to do, what is the engineering and the science actually going to look like. And this is kind of the sort of thing that I've got in my head. This is the James Webb Space Telescope. No, it's not, obviously. This is an Imperial Starship Destroyer. This is the James Webb Telescope. And of course, what you'll have noticed is that they were not that different, okay, in their sort of size. But at least this can give you sort of some sort of an idea. So it's quite interesting to hear John talk earlier actually about the mass of Cassini and Huygens actually being about 6,000 kilos. This is about 6,200, or so they claim. So what we would like to do is obviously get that last final measurement to see whether or not any blows need to be traded, I think, academically, with regards to mass and weight. They usually like doing that sort of thing. But this really is one of the largest sort of satellites and structures that we will ever launch. It has essentially a telescope, a big sort of telescope you can see there with a primary mirror on the side and then a secondary mirror there. And it has a massive heat shield at the bottom. And that heat shield is the size of about a tennis court. Okay, so this is a tennis court size heat shield that has about 5 layers, and each one of these layers eventually will be reflecting out as much heat as it can kind of out of the side of this. It is hand-stitched out of special materials, actually out at NASA, and is able to then attenuate the heat that comes off of our sun by about 1 million times. So if you think that for 1 square meter, we get roughly about 1.398 kilowatts per square meter of energy, it attenuates and reduces that down by about 1 million times. So what does that mean? That means then that on the bottom there, you can see kind of a rough sort of cubic sort of shape, and that cubic sort of shape is the satellite bus, that's the platform, that's where we keep the computers, the communication systems, the batteries, all of those things, and that's meant to sit nice and warm. Except nice and warm, where this satellite is going, is about 85 degrees C, on average, is what they believe. And on the other side of that, the optics and the instrumentation, especially with regards to cameras, spectroscopy devices, other types of systems that are going to be looking up all of these different particles we want to see, will actually be about minus 233 degrees C. Okay, so this is super, super hot one side, really, really cold the other side. And it really has about 4 instruments on top of it. It's got a couple of cameras, and it also has spectrometers as well. And those detectors are able to then look at extremely faint signals. Okay, so again, we're just trying to do the similar sort of things that Hubble has done, but on a slightly bigger scale. One of the instruments in particular is a programmable sort of system, and that sort of has a detector in there that can observe about 100 things at the same time. So it actually does some very special things with regards to the processing that goes on in the computer here. And that's just sort of one of the instruments. They all do wonderful and fantastic things. And I want to kind of give you a rough overview as to what goes inside this, because this is the next big thing that's coming up. So how big is it? Okay, we've already heard about Hubble and the sort of results and images that Hubble can get. And Hubble is shown there, again, next to a standardized unit of a human, showing you roughly how big it is. But the actual James Webb Space Telescope is much, much bigger. The diameter there is about 6.5 meters. Okay, and that really, when we compare that to the Hubble at 2-point-something meters, really starts to tell us something about how much light we can collect. So if we think about, for instance, the actual area of a circle, so we've got pi r squared is that. The dominant term there is the r squared, the radius actually of that lens there that's going to be collecting that light. And this is 2-3 times bigger, so it's going to be collecting 2 to 3 to the squared term, okay, more light actually into this system. So it will be able to then collect 8-9 times-ish the amount of light. Okay? So it's much, much bigger. It can collect much, much more light. And like the Hubble actually goes back and looks at the near infrared to look at the earliest parts of our universe, what we're doing is we're essentially looking back in time. Okay? If we're looking at all this light that's very, very far away, it's just very, very old light. And that, for Hubble, is about 13.8 billion years. It's trying to get as close as you can to the Big Bang, okay? What we believe actually happened at those kind of stages. And with this particular one, we want to be able to do that with a much, much finer degree. We want to go back even further in time to find out what that is. So first, let's just perhaps talk about some of the other differences. The first being is the actual physical location of where this mission will go. Now, this particular drawing up here shows some very, very specific situations that we actually want some of our spacecraft to go to. These are L points, we call them as Lagrangian points. And these are special points where the masses between our interplanetary bodies within our solar system are aligned. So in the same way that we have a geostationary or a geosynchronous spacecraft that is essentially orbiting the Earth at the same rate of the rotation, this essentially follows the same orbits but on a planetary scale. So that L point is a point that is of an equilibrium state, okay? And it means that a satellite can go there and just orbit around it, and they call those halo orbits. Sometimes they do figures of 8 as well. But it means then that you can stay there at those sort of equilibrium points. And what's unique about this one, L2, is that it's on the other side of the sun, which is great because any of the radiation, any of those particles that's coming out of our own star isn't going to affect our instrument. And it means then that we can then go ahead and keep doing more science. It can keep cool. It can keep doing the things we need to do. And that equation kind of in the top is one of the guiding principle equations of how we then work out what masses and forces to find these equilibrium points. Okay, so if those of you that do your physics and those sort of things, these are obviously the classical sort of equations of motion. We can do those for each different planet and each different body. And this is really, really complicated, purely because of the fact, not just because we've got a sun, an Earth, a moon, and then we've got those equilibrium points there, but of course we've got all the other planets too. All of these extra masses suddenly become then and what we call an n-body problem, okay, which is when things start to get a bit more difficult, because then you've got to start adding all these masses, all these extra terms, all these extra distances that, as Abby has alluded to, kind of wibble about a lot. Okay, none of that stuff helps. But it's much, much farther away than Hubble. It's much, much cooler, but it will be quieter, okay? So we'll be able to hopefully have a much better environment to be able to then sense the sort of things that we're looking for. So, what sort of thing do we want to investigate? So missions like COBE and the WMAP satellites were able to look at the sort of heat signatures and the infrared that actually comes from the earliest parts of our solar system. And we can see as far back as we can to maybe around 400,000 after what we believe to be an event that we now know to call the Big Bang. But after that, really, after the Big Bang, you then had essentially a soup of particles. Okay? You had your protons, neutrons, electrons, photons, all of these things bouncing around. And of course, after it happened, everything's very close, everything's very tight, everything's very, very hot. And over periods of time, what happens is they all start to cool. And as things cool, they start to then form their own individual particles and ionized atoms. Now, when you have ionized atoms, it means then that you can then start to collect electrons around you, start to form things, the first elements. So you've then got your hydrogen, you've got helium, and you'll be able to build up from there. And that's kind of where it started. And from that point, though, it allows then photons and electrons to then move around and actually have a system that could then have light travel freely rather than sort of specularly reflecting off of just all random particles floating around each other. That was essentially when we came out of the Dark Ages. Okay? Before that, everything black. And after that, of course, we could then build up bigger structures and, of course, as things cool down even further, into now what we call stars. But the big difference that kind of comes from me when I work, obviously, in a space center and we build spacecraft is how do we get all this stuff down? And Hubble itself generates about 140 megabits of data per week. Okay, so it generates Not that much. I think like a regular 3G kind of system. Maybe 3D is a bit better than that. But the new James Webb Space Telescope is generating gigabits per day. Okay, hideous amount of data that we've got to then download. Okay, so it starts not to just be a very, very big space telescope. It starts to then be a big computing problem. So you've got a ground station on the ground. We're pointing it up at some point in the sky, and we've now got to collect all of this data and put it somewhere. Okay, so for those of you that have got, like myself, I've got a 256 gigabyte sort of hard drive. Yeah, that's full up, like less than, in a day. Okay, we'll be filling these things all up, okay, for a mission that has a lifetime of anywhere from 5 to 10 years. Okay, says usually 5 to 7, usually they last a little bit longer. So we've now got a big data problem as well of how we're going to analyze this data. So that's one of the real special parts of that. The other special part of it is it actually has some deformable mirrors as well on this. So these are the actual coating and beryllium sort of coated with gold on each of these individual plates. And you can see these sort of holes, these pits that you can see inside them. And that is allowing essentially a special actuator to allow the mirror to deform. So if we needed to do certain shapes, certain sizes, certain fields, then we can actually go ahead and do that. So if we notice that, something isn't quite in focus, no problem, we can deform that mirror again, okay? We can't do that at home, okay? But maybe that technology comes later, and we'll all look beautiful in the mirror and symmetrical, etc. Okay? But this is a sort of wonderful thing that you can kind of get from these sort of things. They're starting to think about what is going to give us that resolution, what is that engineering problem that we're going to face when we go out to these places. And the sensors themselves, though, are much, much bigger. So these pieces of silicon are completely ground-free from the rest of the satellites. So the actual detector is a huge block of silicon. You can see it there. And the one that you typically have in your smartphone is maybe a few millimeters kind of square. It's a tiny little sensor. And of course, that tiny little sensor is going to be generating, I don't know, megapixels, tens of megapixels that you get on a new Galaxy or a new iPhone. Other models are available, of course. But you can see there how big some of these sensors are. It's collecting a lot of data. And they put them all together in all of these different configurations that allows us to then do more with them. So for instance, this big gold piece at the top here is essentially a big wheel that has different filters in it. And it has different systems in there to give you slightly different optics or slightly different views from perhaps the same instrument. It means then that you can be a lot more flexible for finding those things. So hopefully when we go somewhere and we go, we didn't think of that thing that we forgot, or we didn't think of that thing that we knew might happen but was really low probability, but of course happened, we can fix it. And some of this is aiming to give us that flexibility. So, how do they build it? This is the kind of piece that really starts to interest me because these are megastructures, okay? And of course, if another alien did see them, they'd probably be alien megastructures too. But in this particular case, we're looking at what we call a solid air-bearing a sort of optical bench that we're having to build. That has to be ultra-flat or ultra-stable. Okay? So these structures that they build are designed to be sort of anti-vibration. You can't sort of have something that goes into space and is then controlled with very, very precise wheels to be able to move its satellite's attitude to point at a particular point in the sky when the rest of the system is shaking. Okay? So they put all these things together in painstaking ways in huge buildings out at JPL, where they then go ahead and test them out in Maryland. And so there's a few more pictures that I want to show you on James Webb because it leads us in quite nicely into some of the things that we discussed earlier. This one, you can kind of see in this picture, like kind of ghosts everywhere. Ghostly pictures. You can see them at the top. You can see the guys kind of at the bottom. And because this one is a false color representation of an ultraviolet image that is taken that is actually looking at contamination. So this one is essentially the equivalent of someone going around with one of them sort of UV sort of lights going around rooms, think CSI, etc., but on a much longer time scale. They want to know who's been touching it, if anyone sneezed, what other grubby things that humans do, what happened and went vaguely near the James Webb Space Telescope. They do this long integration sort of time step, but it gives you that sort of ghostly kind of sense to it. And of course, all these big missions then have to go to all of these big facilities. This is one where it's undergoing acoustic testing. So it has to undergo 150 decibels of acoustic testing, which is amount of energy to be able to push that in, just to see what happens to the mirrors, okay, as they flex and as things vibrate. Just to make sure as well, then that if they need to, they can then calibrate it afterwards. They can reset it back to a set of normal parameters, go ahead and then collect the star, not knowing that one of the mirrors has kind of been bent or broken. So that's kind of James Webb. It's going to be the sort of biggest next piece that is going to be able to look much, much farther into history than we've ever done before. Okay, and that is due for launch in the next 2018-2019 sort of timescale on an Ariane 5. But they're already, of course, starting to look at the next big thing. Okay, of course, there's always got to be one that's bigger and better. Okay, that's just unfortunately what typically happens. And these particular telescopes go even bigger. Again, we think about that area, that pi r squared sort of terminology, to see how far back in we can go, and it just starts to get mind-boggling. So instead of getting a couple of hundred gigabits of data per day, okay, we're starting to look at terabytes, possibly a day, or even measured in hours. Okay, this is the sort of data we're talking about. And it then means that we can then take even finer photos, even finer glimpses into what our history actually was, and how these things started to coalesce, and whether or not these theories of differentiation of what happens with all of the particles at the early stages of the Big Bang actually ring true. And again, it will probably find many, many more stars, planets. They have instruments on there not to just detect the infrared sort of spectrum as well, but they have regular cameras and all sorts of other cameras that can help then understand what these systems are to find all of those perhaps habitable places. So how are we going to do that? These things just keep getting bigger, they get larger, and the main thing that we've been working on really at Surrey is a mission called ARREST, and this is kind of one of those concept drawings of the sort of thing that we kind of need to push to, of how we need to go, yeah, we can keep launching this thing, but at some point, we're not going to have the rocket to be able to do this. Maybe Elon might, but perhaps not everyone will be able to do this thing and maybe not have the budget to do so. So what we would want to do is split that up into then smaller segments and essentially fractionate that spacecraft. Turn it from one big monolithic piece into something there where individually they are all separate individual spacecraft. And we've started to work on this. This is the sort of concept that we want to do for those next generations of satellites. And we work on those here in the UK, and actually with our partners out at NASA in JPL, and also at Caltech in Pasadena as well. And this is the sort of thing that it starts to look like. We're doing kind of a test case to begin with. The test case for our particular mission takes on CubeSat technologies. So you would have heard Sean talk about CubeSats and understanding how these sort of very, very small objects can go actually perhaps quite a long way. And people are trying to understand how and why they can be that useful. And what we want to do is be able to sort of take the CubeSat technologies, put deformable mirrors on them, much like we do, and have a mirror there, but be able to configure them in different ways. So instead of having a fixed way in which we can do things, we can then move things around. So if we wanted a certain telescope configuration, resolution, aperture size, sensor, take away a bad element, put the one over there, have that one do something slightly different, we should be able to do those things. And these are then sort of next technologies that we're starting to see. The one on the left, okay, is something from the International Space Station, a program called Spheres, which I believe is still run out of MIT by a guy called Alvaro. And he is essentially, like probably Sean's already talked about, they've started to put smartphone technology on board these sort of things. And they are testing these sort of formation flying capabilities. They want to know how do we then take these structures, put them together. They also want to know how do you then avoid collisions? How do you want to then prevent the fact that if you get this wrong and you're accelerating too fast, that you're just going to turn this into a huge debris field, okay, which would be awful. The one on the right is the sort of one that we are building at Surrey Space Centre, okay? Doesn't look perhaps as great as the one from NASA, but we get it, okay? These float about on, again, an ultra-flat sort of surface table, and we use all sorts of different types of commercial off-the-shelf technology. And the reason why we do that is, of course, it's accessible, it's cheap. Okay? We want to be able to use these sort of things to be able to then mass produce some of the different things that we want to do. So if we do need to have an optical telescope that needs 300 of these type of elements, that it can actually be producible. We can mass produce them, it can be reliable, we can have a production line. Something very that SSTL and Surrey have been very successful at. Good example of that is the use of, you might notice some logos on some of these circuit boards, is the way that we use COTS. And one of the things that I particularly work on is the hardware and software enabling us to then build and do computing for some of these new missions. So for me, when I see sort of a requirement of 235 gigabits per day, data requirement, what we're going to do with it, etc., I'm like that, yes, give me data, I will do things with this, okay? This is a good problem to have, okay? Rather than the other way round, by saying, actually, we've only got 8 pixels for this thing, there's not enough data here, we can't really make conclusions, okay? For this, we're using Raspberry Pis. There's a Raspberry Pi kind of symbol there, you can just see. And these are sort of commercial ones. These are the industrial grade compute modules. And those I've got to build 6 of these by August, so they can then go on each of the separate individual parts that go onto the REST mission. And this is the sort of optical bench where we do our testing. So this is like a big flat surface where we then have special optical alignment measures. That's me taking a photo in the primary mirror, where we can then test what sort of return we get on the laser. So the Caltech are working on these deformable mirror technologies, really sort of great things that they can do, especially when they do it in real time and they're controlling how they can calibrate this lens. And I'm going, okay, this is interesting. Let's figure out how we can use this in a real mission. What does it need to do? Because for me, I'm part of that sort of engineering sort of line where we want to figure out how to do that. So we've now got this kind of rise of the CubeSat as well, these sort of small things that are becoming capable that can maybe be put together to make larger and bigger structures. And a good example of that, of where then big agencies are taking that seriously, is NASA itself. And this is a mission called MARCO. And MARCO essentially has an entry, descent, and lander mission called InSight. And when it sort of lands down here, during the operations, there will actually be 2 nano satellites that will then have a very, very similar radio link that the James Webb has. Okay? It will be transmitting on X-band and UHF, okay, which are exactly the same sort of bands. They're talking about shrinking that technology down so they can then go, okay, we've got this small stuff now, what can we go and do in the future? So in the future, probably what will happen is science instruments will just keep getting bigger because there's no way around. If you need optics of a certain size, you need that optics of a certain size. But with the electronics, that will start to shrink and get smaller and smaller. And that's what we see on the James Webb one as well. The actual bus size is maybe about 350 kilos in comparison to then the 6 tons, okay, of the rest of the payload. So it's starting to get smaller and smaller. And it then means as well that you can have then people working on them. And these are the sort of risky, the sort of higher risk sort of configurations that people are sort of wondering about. Okay, because they aren't perhaps over-engineered. They are done a lot more rapidly and quickly, and they use a lot more younger people. So how do we go about building these sort of things, and how quick can they actually go? So this is the satellite that we've been working on at Surrey Space Centre called SMESat, and we have something called our soft stack, which is where we put it all together to check everything fits. This is a real-time how quick they work at Surrey. It's not. But this is a sort of time-lapse video of us putting together one of our 3-unit CubeSats that we have in the Space Centre. So we have our own clean rooms, our own chambers, our own pretty much all things now, bar a big radiation source that I would like to use on computers. I still need to go somewhere for those. But it means then that they can be put together in a relatively short period of time. When we actually put these things together, we will want to then check out each individual interface, and we go through different checks as we go through it. So as we start to then plug in a computer to a battery system, you need to check everything's working, like the batteries and voltages working. Okay? Now, obviously, when these things are sort of small, they're simple, we then can do typically much less checking on them. We don't want this to be a very expensive system. So unlike perhaps, for instance, the procedures that the James Webb went through, the procedures are much, much lighter. Okay? But it means then that we can then go ahead and do testing, do things in situ, and do things in a slightly more mobile way because we can hold these things. They are small, they are manageable. But it does allow us to then push through and then fit things together. That's just the boom going on that has a magnetometer in it. I guess they went for lunch then. How dare they? But NASA are doing this on lots of missions. These are all of the CubeSat missions that they actually have now. And of course, one of the ones that I've talked about is MARCO in this top corner here, Inspire and Lunar Flashlight. These are ones that are going to be going to the moon as well. But they're all technology demonstrators. They're not going to be doing the big science that you expect. from the big missions. Okay? Those are two separate things, but they are, again, complementary, because they want to be used to educate our young people, to be able to think differently, to do something slightly differently, but also to do all of that technology demonstration that we need for those bigger missions so that we can optimize, be more efficient, go farther. And of course, they've got a timeline for all these things. Okay? We can then figure out where things happen. And this is R1. R1's been kicked off, and because we've been working a long time on this, it's just got a long bar. So R1 plans to be launched in 2019 with an Indian launch. We're still waiting to sign that contract, but other ones are going up. So Marco's going to be going up in 2018, okay? Roughly the same time as James Webb. The difference being, though, is that James Webb kind of started in sort of the mid-late 90s, when they were really sort of starting it out, and some of the CubeSats, like Marco, started in about 2015, okay? And at a fraction of the budget. So this is sort of the sort of size, it's roughly sort of size like this sort of big, of a satellite. And of course, we don't necessarily have the same types of budgets as well. So we can do, hopefully, quicker and faster things with these missions to try and figure out what will happen next. And that is actually what we see happening now. So when we sort of ask our sort of self, what is next? This is next, okay? And this is 104 CubeSats being deployed from a PSLV launcher on February 29th this year. That is for a company called Planet Labs, okay? And I've sped this up. It doesn't happen like that, okay? I just wanted to shorten this down to a 30-second window. But it happens over a course of hours. But they'll be shooting out these CubeSats to do multiple missions. In their case, they want to image more rapidly on certain points on the ground. So instead of us having to wait to go around the Earth to get back to the same point, they're just going, well, we can just launch more of them, make them smaller, make them cheaper, and then we can get access to that data. Technology is consistently shrinking, getting more capable. Let's use it. So people are now still thinking about mega constellations. And the problem with mega constellations is, and we don't have time for this, is that they can bring up their own new sets of problems, okay, of actually how many satellites we launch versus what we do with them ethically if and when they come down. Some of them don't. They're up there so long that they'll be up there for centuries, even millennia. And so we need to start then thinking about how do we then build these structures up? This is a simulation that I did when the work that I do in relative formation flying, so how you get these things to move around each other, that allows me to then keep these things in stable configurations. In particular, this was to counter the sort of effects and the perturbations that we had from all those masses that we have. So in particular, I was looking at the oblateness of the Earth, the Moon, the Sun, all of those big major sort of pieces that we worry about for the gravity fields. But we're going to need to know how to do this. If we're going to be building the sort of next generation of superstructures to look out farther into the atmosphere, to look out farther into our solar system, then we're going to need to know how to do these things in a much more compact and smaller way. And with that, I think I'm roughly done. Thank you for your attention. Okay.
Perhaps we have time for one quick question for Chris.
Yeah, it's the guy here.
Yeah, that Hubble Space Telescope was what serviced that 9 years ago, exactly.
Uh-huh.
How's that coping today? So we want to overlap with JWS, don't we?
Yes, yeah. So the question really is, if I understand correctly, actually, can you want to repeat the question? Because it was like talking about servicing.
The Hubble Space Telescope was last serviced in 2009. May, so how is that coping today with where it's in space?
Pass.
Will it still outlive?
Yeah, Hubble will likely outlive what they need it to do. The James Webb has a quite, from the conversations that I have about James Webb, the concept of operations, getting them to an operational state is much, much quicker than they had before for Hubble. So it's just getting them to then that L2 point is going to be the main problem. But they'll be doing tests in LEO before it then goes to do swing-bys by the moon. Each of these sort of phases allows them to kind of tick really big boxes off on their instruments. So there'll be plenty of overlap from what I see on these timelines.
Thanks very much indeed, Chris.
Yeah, thank you very much.